So, okay. So let let's do this kind of example. So this is like a simplified version of the assignment, right? So the setup would be like that. I have a function that's run, and that means run for 1 minute. And the rule is if a star was offered, uh, add 3 hedons for a run. If a star is not offered, add 2 hedons. So that's the whole thing, right? So if I say run, and then I say like get current hedons, and that's supposed to be 1. And then if I do like 2 runs, sorry, not 1, it's 2. So 2 runs, and then get current hedons would be at this point 6. And then if I do an offer star, and then I do a run right away, then that will be 9. Does that make sense as like a set of rules? Yeah. All right. So, okay. So let me now implement it. So I'll do this. So I'm going to have my initialize. So I don't really need a lot of information here. I just need to know my current count of the hedons. That's it, right? And initially, it's going to be 0. Yeah, if we go to like the line, pretty much the line. All right. So I'll okay, I guess like you guys are making the noise. Okay. I'll just like recap. So I was doing like a simplified example that's like project 1. So the rule is kind of like this. So we have run and we have offer star. And the rule is that run just means run for 1 minute. It's always 1 minute. And then you get 2 hedons if you are not using a star, and you get 3 hedons if you are using a star. Right? So, okay. Yeah.
So like
Yeah.
you hit an addition.
I mean, what they mean is you get I understand what you're saying. Like I'll just change it to earn. So I was just like making it up on the spot. So yeah. So the system here is if you were offered a star and then you run and then you do like get current hedons. So now it's supposed to be 9 because you earned 3 from the star. Okay, so current hedons initially would be 0. And also star offered initially would be false. So I'll make a variable that's like star offered. And I'll say kind of initially there is no star offered. All right. So, okay. So now I just need like run and get current hedons. So get current hedons is super easy. It's just return hedons, right? And now I got to do run. So the idea here is, oh, I didn't do offer star yet. So, okay, so offer star. So that should flip star offered, right? So does this logic make sense to everyone? So what I'm saying is like offer star. So in the project, you actually got to track when it was offered. Here, it's like if it was offered, like use it or lose it anyways, right? So, okay. So now I got to write run in a way that's consistent with, sorry, does this make sense to everyone? Okay. So now I got to do run in a way that's consistent with the code so far. So the easy part is saying, you know, like if star offered, then I am going to add 3. And so current hidden, I'm updating. So that means that it's got to be global. No, so that's the same, right? So saying if start offered is the same as saying if start offered is equal to true. And that's just because like, when is this true? Well, it's true when star offered is true, and it's false when it's false. So so when is this true? Well, it's true when it's true, it's false when it's false. So it's the same. Okay. So all right. So if a star is not offered, then we are adding 2. So the other thing that happens is run always spends time. So that means that if a star was offered before, it's not offered now. So we also got to update star offered. So whatever happened, a star is not offered anymore. When you offer it again, you can, but it's not offered anymore. Yeah.
Star offer function and star taken function.
Well, so here I don't have like a star taken. So I have like a status, like was the star just offered, and offer star, which is like a notification that says you got star. So you're referring, I think, to star can be taken in the project, which says, was there a star that was offered just now? And can I use it because I'm not bored with stars? Right. So that's like a hypothetical question. Like if I were to do the activity, then is there a star that's offered for this activity that I can use right now? And am I not bored with stars? Right. So here it's like an action that's like a notification that the star will. Does that make sense? Yeah. Okay. So all right. So here I'll just do print. And I'll make sure that it makes sense. Star offered is not fine. So star offered line 17. Yeah, so I did not star offered equals, so I did not call initialize. Okay. So that does it. So the mechanism here was we're saying we'll keep star offered updated. And the way it's updated is if I call offer star, I flip it to true. And then every time I run, I say, okay, that's gone. Okay. So that is some of the stuff that you need. So it works the same way in project 1 if you wanted to. The other thing that you got to keep track of in project 1, though, is when were stars offered. And that's because you also need to know whether there were 3 stars offered in the last 2 hours. Does that make sense? So let's do let's do a clock. So here, kind of the way the clock works is like the run is always 1 minute. By the way, it's all streamed. You can go to YouTube and get a nicer screenshot, if you want. But okay, so 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 here I'll say clock is equal to clock plus 1. So this is just because like the way I set it up, the run always takes 1 minute. So like if I had like a custom duration, then it would be different, right? So okay, so got to make it global, of course. So now I also have a clock, so that's nice. So that's like not used. So if we want to use it, then we got to make up some kind of rule about kind of how could the clock be used. So you can say, for example, right? So you can say like in the first 360 minutes, you earn hedons. After that, you do. So that's like a simple one, right? So you would just say, okay, so that only applies if the clock is smaller than 360. Otherwise, you're out of luck. Okay, so that does not have a parallel in project one. Like there is no rule like that in project one. So what you do have in project one is a rule. Well, there's two things, right? So you got to keep track of how much you just ran in the same way that here we're keeping track of what the star offered just now. So that's the same, right? Because so you need to know, have I just run 70 minutes? Because there is a calculation of, yeah. So that's the same, right? So here we're saying, did I just call offer star? And the way I know is star offered was flipped to true. And I reset it back to false. The other way in which we need to use the time is we need to know when was the last time the star was offered and when was the time before last that the star was offered. The way we can use it is if the difference between the current time and the time of the star before last is less than 2 hours, then you become bored with stars. So keeping track of that is kind of similar to the undo example from lab 2, where you had to keep track of the value before. Okay, does that make sense? All right, hopefully that helped? Yeah, okay. All right, okay, so any project questions or we'll switch to the lab? Okay, we're doing the lab. So, okay. So, okay. So we have this bit of code that generates secrets. Okay, so I'm copying and pasting it. So here, like, I don't think it's actually bad. So like, if you like did a screenshot and pasted it to ChatGPT, it would give you like nice code. But I don't without the solution. So you could ask for the solution. But I think it's actually good because like that's like a compromise between like giving you code and like just giving you the solution. So at least you need to like keep track of how the indentation is supposed to work. So okay, so we kind of did it in lecture, and we kind of said that like the details of the syntax here are not important so much. What isn't generate data missing. Okay, so generate data needs the number of points. So that's 100. So we ran this. So y now is like this. So it's just like the sine of 2.5 times theta. So we now want to plot it. So I'll get my x over here as well. And I plot x and y. So PLT show. That's 100. So that's my sine function. Does that make sense? So that's kind of the same as the lecture. So now what we want to do is we want to generate. So here we generated the data. So I also want to generate kind of the noisy data. And then I want to section. So, okay, so I'll generate the noisy one. So that looks like this. So now what I want to do is I want to try to match the kind of generated noisy data to actual data. So that is given. So if I set A to something, for example, 2.6, so I can compute the sum of square differences and print the sum of square differences, and it's 8. So the correct, like the secret A is 2.5. So if I compute that, then the error becomes really small. If I am off by 0.1 again, then it's like this. I'm off by more, then the distance becomes larger. Okay, so what I'm trying to do here is to pretend that I don't know the secret A and try to find it. So, okay, so how can we do it? So this is like the way it's set. So I'll just say, okay, so I'll just try different possible A's. So I'll start with like a possible A that's like -5. And I'll increase A by like 0.05 or something every time. And here, for now, just like in lecture, I'll print A and I'll print SSD. So that's like this. So this is saying for A that's like 2.4, it's like this. For A that's like this. For A that's like this. So this is the best one. So like the sum of square differences is as small as possible. So now what's left to do is to get back to this one. So like, how do I get it? So right now, what I do is just like I keep incrementing A and just printing. I can also just keep track of what was the best A that I've seen so far, right? So I'll do it. So I'll say like best SSD. Initially, I'll make it like huge. So like make it like 1 with 20 zeros. And then I'll say, okay, so if this SSD is better than the best one, then my best A is my current A. So here I'll print A and I'll print best A and I'll print SSD. Oh, sorry, I did not update SSD. So this is like this, right? So I start with saying, okay, let me just restart it so that you don't have to scroll to a previous example. So I start with guessing -5 and saying, okay, -5 is the best A that they've seen. And then I go to this, -5 is still the best one that they've seen because this SSD is like a little bit larger, right? So that keeps going. So it's not going to be like monotonic because if you're way off, then it could be whatever, right? So when you get closer to the actual correct guess, so here, like we're guessing like 2, and we're saying, okay, like here it's still this. So now we actually keep getting closer to the correct guess. So like we're almost there. So the best A keeps updating because you keep getting smaller and smaller SSDs, right? So that happens up until the point where you get the best SSD, which you get over here. And that's the best one. That's basically the correct guess, right? So from now on, the best A is going to keep being the same because you're not going to get better than 2.49. Make sense? So, okay. So now we have the best A. So all that's left is to also plot the best Y. So we'll say, so best Y is going to be generate data best A 100, right? And now we're going to say, okay, so we have the best Y, so we'll just plot X and best Y. Okay.
So, for, so since the code is A equals to A plus 0.05, is it just because you want this code to run for like tens of times?
Well, it's not, I mean, you did you compute it? It's about that. So it's just that I want to say, okay, like I'm starting with my guesses with -5, and then I'll try -4, -4.95, -4.9, -4.85, and so on. And the way I do it is I start with A being -5, and then I increase it by a little bit, increase it by a little bit more, and so on. Cool. Okay, for your screenshotting pleasure. All right. Okay, does that make sense? Yeah.
Set best SSD again to 1 to the power like 10 to the 20.
So it's just I want to set it to be initially something extremely large.
Oh.
So that when I see so like that's like a bit of a hack, right? Because like you could imagine that it would be this large, like I don't know. So in principle, like if you wanted to be nice about it, what you would do is you would compute this, the once. And then it's like the best SSD that we've seen thus far is like -5. But like I kind of prefer the hack this way because like this is like adding complication. All right. Is this all good? All right. Are we doing the hats now? So okay. So right. All right. Okay, so one thing is that like in the PDF, the ticks are like rendered wrong. So they're like the curvy ones. You want the straight ones. Like Python will just complain about the curvy ones. Like this. Hats. Okay. So let me quickly go over generate hats in terms of what it does. This, by the way, should be indented. So what we're saying is generate a random number between 0 and 1. And then if it's less than half, then we append W. More than if it's more greater or equal than half, then we append it. So that means like with probability 50%, we append W. With probability 50%, we append B. So what you get is random W and Bs with kind of a coin flip probability of W or B. Does that make sense, everyone? Okay. So now we want to count the number of white hats in the list hats. So let's do that. So I can say count initially is 0. And then, so hats is going to look like this, right? W, B, W, whatever, right? So what you can say is, okay, for hats and hats, so that makes it so that hat is W and then hat is B and then hat is W again. And then what we want to say is, if the hat is white, increase the count. If it's not, then don't. After you're done, so you went through all the hats. You incremented the count every time that you saw a white one. Now count contains the number of white hats. So that's all there is to it. Okay. So now what we want to do is we want to say, okay, so we're making the guesses. So the rule for the guesses is like that. So we pre-decided that the students are assuming that there is an even number of white hats. So then we're saying, okay, so this person, what do they see? And the answer is they see one white hat. This person, what do they see? They see 2, because that's the other ones. What does this person see? They see 1. So how do we know? Well, one way to do it is to say, well, there are 2 white hats in total. If I'm wearing a white hat, I see 2 minus 1. If I'm wearing a black hat, I see 2, because I don't see my own, right? So let's construct the guesses. So the way I'll do it is I'll say 4 hats and hats. So compute how many hats, right? So what we're saying is if the hat is white, then white hats seen is number of white hats minus 1. Otherwise, the number of white hats seen is just the number of white hats. Does that make sense? So like we're looking like for the person we're looking at, this is how many they see. And then the rule is they assume that the number of white hats in total is even. So if they see an odd number of white hats, then they guess that they're white. Otherwise, they guess they're black. So it's odd, we guess white. So what does it mean that we guess? We append white to guesses. Otherwise, we append black. We're done, return guesses. So again, like the logic here is like this. So you start with guesses being empty. And then you keep appending either white or black, right? So you want, like in this case, the guess, so they're guessing that the number of whites is even and they're correct in this case. So this person would guess white, and this person would guess black, and this person would guess white. And the way it would go is guesses initially would be empty, and then it will become this, and then it will become this, and then it will become this. Right? So that's kind of what we want. And the way we do it is we say, okay, go through the hats. So this would be W, B, W. And then the logic here just makes it so that in this case, the guess is correct. Is that making sense? Sorry. Okay. All right, so let's test it. So we haven't done the are all guesses correct, but we have done everything else. So hats are like this and guesses are like this in this case. So every time you generate different hats and different guesses. And the way it works is like, that's the beauty of it, is that if they guess correctly that the number of white hats is even, then they all guess right. So sometimes they all guess right. And sometimes they all guess wrong, because if they guess wrong, then everyone gets it wrong. Does that make sense? So, okay. So all we need to say is our all guess is correct. So in Python, like there is a trick to it, which you can use. So you can just compare lists the way you compare integers. So those would be not equal and those would be equal. So technically you can just say return hats is the same as guesses. So, and that's like the same trick as before, like when is this true? Well, it's true when hats is the same as guesses, and it's false when hats is not the same as guesses. And that's exactly what the function is supposed to do anyways. So you're kind of done. So you can, however, if you remember kind of the example with the major, like with the salaries, you can kind of stick hats and guesses together and see whether each one matches. So the way you would do it is you'd say for I in range length of hats. So here, what you're doing is like I is going to be 0, and then 1, and then 2, and then 3, and so on. So the logic here would be that you want to say, if there is ever a mismatch, then you know that the answer is definitely false, because even one mismatch means that not all guesses are correct. So we'll do that. And then like a common thing that people are sometimes tempted to do is they say else return true. That's not right. And the reason it's not right is that just because hats at 0 is equal to guesses at 0, it doesn't mean that everything else matches. But if you went through everything and you never got to the point of returning false, then you return true. Okay. So that's kind of the longer way of doing it. So now we're done. And as you see, half the time, well, you have to check, of course, but half the time they all get A pluses, and half the time they'll fail. And so one of the nice things about it is that, like, where's the cheating? Like, it seems kind of like magic that you can do it. but the cheating is actually like in the setup, right? So they didn't actually change the probability of failing so much as they just made it so that they either all fail or pass. It's still the case that, you know, the probability of you failing is 50%, the same way as if the rule was that, like, you guess right, you pass, you guess wrong, you fail. You could do that without any mechanism. So the mechanism just makes it so that their guesses are like self-consistent. It doesn't actually, with this solution, doesn't actually increase the average probability of passing. So that's like that's like the fakery of like, it seems impressive, but actually all they did is just like made it so that either they all pass or they all fail. It just happens that Professor Evil set the rules so that they all fail, even if one guess is incorrect. All right. And does that make sense? All right. So question? Yeah. So we're doing GCD. So this is called like exhaustive search. That means that you like check every possibility. That's what exhaustive search means. So the idea here is we just keep trying to say, okay, like, is n divisible by this, and m divisible by this, divisible by this, and so on. And like the largest one is our answer because we want the greatest common divisor. Okay. So how can we do it? So first of all, like, what does it mean that D is a divisor? So that is just n mod D is equal to 0, and also n mod mod D is equal to 0, right? So if that's the situation, then D is a divisor of both. If not, then not, right? So now all we got to do is we just got to go through all the possible Ds and see what the largest one is. So we'll say, okay, so current best, so same approach. So like current best D is going to be 1. And then we'll just try every possible one, and we'll see if we find the best one. So we'll say for D in range, so here we got to start with 1 because you cannot divide by 0, that will just crash. We start with 1. So we go up to, so basically like the greatest common divisor cannot be greater than either one of the numbers, right? So in Python, so like you could of course like write your own minimum function, but minimum is actually built in, so we'll just use it. So it's like very easy to write as well. It's like if A is greater than B, return A, otherwise return B, right? So so minimum here works, and we go up to the minimum of n and m inclusive, right? So it's possible that the greatest common divisor is 1 of n or m. So we got to go up to the actual minimum, not up to the minimum minus 1. So that's why the plus 1. And now we say if it's a divisor. So if that is true, then the current one gets updated. If not, then no. After we're done, we just return the best one. So the other way of doing it is like you could say, okay, like I don't want to go from bottom to top, I want to go from top to bottom. Right. So how do you do it? So if you remember, you can actually set it up with range. And that way, so if you go from top to bottom, you don't have to keep looking. Like if you find a divisor, that's the best one, right? Because you're going from the largest to the smallest. So we'll just do that. So for D in range, so you start with the minimum of n and m. Don't need the plus 1 because when you start with it, it's like the exact one that you start with. And we go down to 0 in steps of -1. And if it's a divisor, then we just return. So here, you don't really need to say anything because 1 is definitely a divisor. Like like every number is divisible by 1. And you'll get to 1. So even though like it looks like what if you didn't return, you'll definitely return because you're going down to 1. So that's it. Does that make sense? Yeah. Because we're going from the largest possible one, right? So it cannot be larger than the minimum of n and m. And we're first checking the largest one, then we're checking the next largest one that's still possible, the next largest one that's still possible, and so on. And we return right away once we found. So because we're looking from the largest to the smallest, the first one that we encounter that works is the right answer. So here, right, we keep saying if it's a divisor, then update. Right? So, and we keep going. So if you find the larger one, we update. Okay. Yeah. Yeah. So if you remember what this does is we're going, so D first it's this, and that's this -1, and then -2, and so on. So this is like steps of -1. So kind of range, just like as an example, so like range from 5 to 0 in steps of -1 is like 5, 4, 3, 2, 1, 0. Well, just 1. Right. So it's like go from here down to here in steps of -1. So you can kind of generalize it. You can say, okay. So you can say something like this. So this would be like steps of -2. So this would be like 5, 3, 1. Yeah. I think that's the last one.
Strings about exams.
Yeah.
Are we writing close on paper?
Yes.
So we won't have time to debug, right?
I mean, so you can kind of trace the code on paper. Like it's true that like that's a disadvantage. I will say, so I came back to U of T in 2020, so that's like the COVID year. And that year we wrote, like obviously like everything was online, right? And I will not say that people were happier. And the reason, maybe they had like long COVID or whatever, but like the reason is that basically there is a trade-off, right? So if you are expected to debug, then the code is expected to run. Which is actually like harder in a way, because like if you write it on paper, like of course, like you make a small typo, like everyone does, right? Like that's expected. And there's no expectation that like if it's like a small typo, okay, like it doesn't work at all. Whereas like if it's done online, then yeah, like you can debug, but the downside is you must debug. So
if you do happen to write it, and then say, for example, after like an if, and then you forgot the comment.
Yeah, so so you can look at the marking schemes for previous tests. So like it's all kind of written out if you look at the solutions. So and the answer is it kind of depends on the question, right? So like if some questions, like the answer is kind of a one-liner, and then like yeah, like if you got something wrong in the one-liner, well, so like on the other hand, if it's like, you know, the last question where like on the midterm, like the last question would be probably like, I mean, some people write like longer answers than they could, but it's probably like the shortest possible answer is like 15 lines or something. And then like, yeah, like we don't care if you forget the column if like everything else is right. So it depends on the question.
like when marking like the written answers, do like the markers just like where you're coding on a computer and like on it, or like do they like trace?
So like, like they could be either, ordinarily, no. So like ordinarily, kind of someone who's like somewhat experienced can kind of like take a look and get a good sense of whether the answer is correct or not, especially like they're grading like usually like there's like 2 or 3 TAs who are grading the same question for the entire class. So like you get a lot of experience pretty fast doing that, right? So ordinarily no. Sometimes, like when we grade, like sometimes it's online, sometimes we all sit in the same room. And like sometimes you see someone like staring at their phones, like I know what's going on there, and they do type it because it's like hard, but that's like not the usual. Not like usually you can kind of glance at it and say, yeah, like seems right, or say this is like a common issue that I've seen a million times before, so I know that's like a -2 or whatever.
But that's like our phone.
No. So if you look, like there's like instructions. So if you look at like very old midterms, I used to ask like one question, like write a docstring or something. I stopped doing it, just because it's like it's not practice. Like I guess so like grading it consistently is like just impossible. So yeah. So so my regular office hours is Monday. I'll announce. So I don't know if I can do it tomorrow. I'll definitely have some over the weekend. Yeah. Well, you got like the project is due soon. Yeah. So I'll announce. Yeah. So like my regular office hours are Monday 5 o'clock. Yeah. So it's like 5 to 6:15. So if you show up at 6:10, then we can talk. And if there's like more people at 6, I'll stay until all the questions are answered. So yes, it's like 5. It's like officially 5 to 6:15 with, and like please come like so that they don't sit around with like nobody there. But like if you come before 6:15, or if you email me that you want to come later, then that's also possible. Yeah, the marking scheme is we have I forget how many, like 400 test cases, and then your mark is the number of test cases that you pass divided by 400. So we'll reveal kind of when you pre-submit, currently you see 4, I believe. So we'll reveal everything else tomorrow. And then
The rest of the test.
yeah, and you can pre-check whether you passed or not. You can resubmit.
It's like other projects later on will also kind of be released all over.
I do it differently every year, so I like haven't like pre-decided. So like there is a trade-off, right? Because like if they release all 400, then it's not pleasant for you as well, because like you see that you didn't get it right, so like you can kind of force yourself to like yeah. That there is a limit. So like especially like like if you see like a person who's like like they passed like 399, but like, they won the 400th one and they like spend 10 hours debugging. That might not be ideal. And it's also like takes up time in office hours and stuff, which like of course we want to spend time in office hours, but there is a limit. We also, the other trade-off, which is like the more serious thing, is that we kind of want you to write your own test cases rather than just give everything out, because that's kind of a more realistic situation where you don't actually have test cases written for you. So it's a trade-off. So sometimes I kind of feel like posting everything. Sometimes I feel like not. So this year I'm doing kind of like a halfway thing where I post them but not right away. Yeah.
I have a question about like line 25 of the main density where
Okay.
it says 4 hot in times. If we were to change hot to just any area like I or J, like would it make a difference?
So as long as you're consistent, right? So like this must match this. But yeah, totally. Like this could be like whatever, and then you make it consistent. It's good.
Size is the list, it's just automatically taking like the length of the.
Sorry, I can't hear it.
It's like it's just automatically taking the length of that list.
So not quite. So there's two ways of going through a list, right? So one way is you say like L is this, and then you say like for E and L. And then the other way is for I in range length of L. And you're saying L at I, right? So this is really like I is like 0, 1, 2, 3. And then like you need the length because you want to go up to length of L minus 1. This one is more like just put 5 in E and then 6 in E and then 7 in E. So like implicitly, it kind of implies the length, but it's more like put every element into E in turn.
Just scroll up to the top where we randomly, how do we like tell it to only generate a random number between 0 and 1?
So that's just what random does, right?
Oh.
That's just its job. So the kind of, in a way, the better question is how do you do something else? And like you can actually like give it a range, or you can just like stretch it like this. So if you like multiply it, then it stretches from 0 up to 10.
Yeah.